All right. Well, hello and welcome to the next episode of 3D and 30. Today, we're going to be talking about one of the barriers to entry or barriers to adoption for metal additive manufacturing, and that's specifically around the skill sets needed to set up a successful build. Even for engineers with vast experience, like you're going to meet Daniel today, who worked for Velo 3D, these geometries and interactions for cutting edge products can be challenging, and trying to set them up to have first build success is not always trivial. And sometimes it can lead to surprises. Nobody likes surprises. So, what if there was a way to predict success? What if there was a way to model this? So, one of our partners on the software side is working on just this problem. PanOptimization is a software company. You're going to learn more about them today. And they are working toward a deep understanding of the process using the actual export from our preprint software, using the slice file to go in and analyze the print with detailed instructions, figure out what's going to go on, and isolate issues and tell you if you need to make a correction or tell you if your build is likely to succeed. So to learn more about this solution, we're going to bring on a couple people today. Pan Michaleris, he's the founder and CEO of PanOptimization. Welcome, Pan. Erik, Denlinger, he is a co-founder and chief engineer of PanOptimization. And our own Velo 3D, Daniel Driscoll, application development engineer, who has a lot of experience working with this solution specifically with in concert with the Velo 3D application. So also, before we get started, as a reminder, this is a live session. We'd love to hear from you. So please submit your questions at any time. We will try to take the questions as soon as they come in. Sometimes there's a little bit of a delay, or sometimes we're finishing a thought, but we will definitely try and address them in a timely manner. So first off, let's learn a little bit about our panelists, Pan, Erik, and Daniel. Welcome to the show. Pan, can you tell us a little bit about your background?
Yeah, I was a professor at Penn State University for 19 years. I was working there on computational mechanics. While I was at Penn State, I had a startup company called Pan Computing, where we developed cubes. That was the first thermomechanical process simulation software for additive. Pan Computing was acquired by Autodesk. Cubes became NetFab simulation. Ended up working 5 years at Autodesk, and then tried retirement. But then soon I realized there was a business opportunity, which was the limitation of the previous generation, I would call software for additive. They couldn't address the complexity of the geometries people want to print today. And then I started PanOptimization with the objective of addressing those needs.
And how did you meet Erik? I was kind of curious what the background is between you and Erik.
Yeah, I think Erik was first undergraduate student of mine at Penn State, then was graduate student, then was first employee of Pan Computing, and then we all went together at Autodesk. So that's how.
I think we've known each other for probably 15 years.
Yeah.
So Erik, about you, I'd love to hear about your background too.
Yes, I'm a mechanical engineer by trade. I have well over a decade of experience in finite elements and thermomechanical modeling. I was the first employee of Pan's previous startup, Pan Computing. I was a principal engineer at Autodesk for a number of years, and then I decided to come along to Pan's new venture here at PanOptimization. So a lot of resume overlap with Pan.
Nice. And Daniel, I know you pretty well, but some of our audience might. What's your role at Velo 3D, and what do you do on kind of a day-to-day basis?
So a lot of what I do is helping people set up parts and setting up parts for customers and printing things, essentially. So advising everybody on how to have more success with the parts and with the technology, and figuring out how to solve the problems that everyone's encountering. And there are some pretty substantial problems with everything, right, as we try to make these larger and more complex parts and make them faster. And so that's where we sort of came together in this.
Perfect. Well, let's learn a little bit more about PanOptimization as a company. Pan, can you give us a bit of a summary of your company?
Yeah, soon we'll be starting our third year of operations. The PanX is pretty much an entirely new software, which is based in brand new software architecture. And that allows us to simulate and optimize process parts of any scale and complexity for additive. There's 3 groups of key technologies at our software, PanX. And one is it uses very low memory and it's highly parallelized. This is making the software very fast and efficient. It is primarily achieved by what we call periodic adaptivity. For example, the software can generate meshes of hundreds of millions of nodes where legacy software couldn't. The next component is there's a new multigrade equation solver. And what this thing enables is solving those extremely high count node number meshes. And this gives the software unlimited scalability. And the last component is adjoint sensitivity, which enables true optimization for additive. The adjoint sensitivity is a technology similar to what you have in topology optimization, but it is in PanX, it is designed and used for process simulation.
So, Erik, we've kind of been mentioning a bit about process simulation. It's not the first time I've heard of it in the context of additive, but can you kind of give us a high-level view of how engineers are looking to solve issues with process simulation?
Sure. So, I mean, what the term refers to, additive simulation, is typically using finite elements to predict temperature, distortion, and stress that accumulates during the manufacturing of the part and can cause all sorts of different failure modes and defects. So there's quite a lot of commercial tools available to deal with those types of problems, and there's probably literally tens of thousands of published academic works explaining how to solve those problems. But where the market need where the market need that wasn't being met was doing it at the scale that that Velo needs to do it at. So for example, the 3 pillars Pan showed, the first question we needed to answer was, how do you even generate a finite element mesh for parts like this? It's not that they're a little bit bigger than what the other tools can model. It's that they're 100 times bigger from an FEA perspective than what the parts can model. Just generating an FEA mesh is completely out of reach for any existing FEA tool. We need to develop entirely new technology just to solve that first component. And then the 2 other questions that we sought to answer were then, okay, once you have a mesh, how do you actually simulate that? Now you've got 600 million nodes in your FEA mesh. How do you predict distortions on something like that? And then the third component is, how do you optimize something like that? How do you improve the print outcome? So those are kind of the 3 buckets that these problems fall into from a additive simulation perspective.
You know, we've kind of talked, you mentioned heat, you mentioned stress, and some people may be familiar with what Velo 3D does, but in terms of our specific technology and laser powder bed fusion, Daniel, can you give just a little bit about how this process works and why heat and stress become such a challenge?
Yeah, sure. So every time that you lay down a fresh layer of powder, you go and trace your part out with the laser, you're creating tons of little melt pools, right? And every one of those melt pools, as it solidifies, is going to shrink, right? And so you're adding a ton of heat to the part locally, and just over time, the part is in a powder bed, and powder is actually a really terrible conductor, even though it's metal. And so it's thermally insulated. You're adding a bunch of heat, and every little melt pool is wanting to shrink and pull and move the part in different ways. And so as you have different geometries and different shapes in, you know, X, Y, and Z, all of it wants to pull in different directions. And so that all leads to somewhat predictable, but not something where you can just put simple numbers to it.
Yeah, it's pretty complex phenomenon. I think that's a good high level explanation of it. And these problems are obviously, this is not unique to Velo. Obviously, anybody printing a metal part has these problems. I think you guys have been extremely proactive in acknowledging and trying to help the end users address the problems.
Well, and then we've got kind of the spectrum of alloys, for all the way from types of aluminums to types of coppers, with all these different heat conduction and different melt temperatures. And I imagine the complexity is pretty high. Erik, I want to touch on something that was mentioned before, multi-grid modeling. It sounds like that's a bit of a differentiator for you and the way you approach the problem.
Yeah, it's one of the three main pillars that Pan had touched on. So where the multi-grid modeling comes up is that I said the first challenge is how do you create an FEA mesh that's 100 times larger than any other FEA mesh that anyone's seen or made, and that was a big hurdle. And we started working on these questions. We didn't know if there were answers to these questions of can you mesh, can you solve, can you optimize. It was a real it was a real gamble to look into these things. So then where the multi-grid comes in is in point two. So now we have a big mesh. How do we solve it? So what multi-grid allows you to do is predict stresses, distortions, and strains in a way that is extremely scalable. So it'll scale to even the largest, most complex geometry. You could do a full volume heat exchanger, and it'll allow you to resolve all of the finest details and predict how the entire thing is gonna behave. And one of the things that makes it unique is that anybody who's run FEA models before is probably aware that you run an FEA model and it takes 2 hours. You go back, you run an FEA model that's twice as big, doesn't take 4 hours, takes 8 or more hours. You do something twice as big again, might take 60 hours. So the computational performance explodes as the models get bigger. What our multi-grid model does is it allows compute performance to scale linearly with the problem size. So it gets around that computational explosion problem. And then the next thing that people want to know is, well, you must pay some sort of accuracy penalty for that if the performance is so much better, but it's not true. So the multi-grid model will actually get you a higher accuracy, higher resolution prediction than a traditional FEA model at any scale and on extremely modest computational resources. I think that's the best high-level, non-technical description I can give. And for technically minded people on the call that say that something that achieves all of those seemingly contradictory things sounds like something, it sounds like a dubious claim on the surface. I would urge you to just check out the PanOptimization.com has more detail than that. If you want more detail than that, you can reach out to us directly, and I'm happy to have a hour-long conversation with you where we take an even more technical deep dive into that, because part of this is convincing people that there really is an underlying technology that makes that all possible.
And it kind of want to just show some of these parts. I mean, this is actually a part that Daniel designed, but we've gone through the steps here and got some images. Now this part is Daniel, this is about 8 inches tall, roughly.
Yeah, about that.
Definitely highlighting those thin walls and that complex structure. Kind of on the other end of the spectrum now is another part, muzzle brake, and this one's much larger. Do you know approximately sizes on this?
Yeah, that thing's probably about 50 inches tall.
Yeah, that's very, very big. So it fits in the palm of your hand, and you're not going to move this without a forklift type of structures. And both of them have gone through the simulation. And then we've got kind of one of the products that your software is working on. Erik, can you walk us through a little bit about what this is showing us?
This is just showing distortion on that 8-inch tall part. So I think the things to note is this is an actual FEA mesh. So everything, if you zoomed in far, you'd see that we're using a fine voxel to resolve all of those features. So there's those features have to be resolved in the finite element mesh if you're going to get a distortion and stress prediction, even on those small holes or those thin walls. So I think the main thing to note here is this is the FEA mesh. There's no tricks. We're not using a very coarse mesh and then mapping the results back to the surface or anything like that. The detail is actually resolved, and that's why when we see us posting pictures of these heat exchangers and it shows 400 million nodes, you say, how is that? How can that be? Well, it is.
Yeah, the detail on that is amazing. It looks almost exactly like the part. Like there's almost no resolution loss or anything.
We've done way cooler. Daniel and I have worked on way cooler things than that. We just don't have permission to share them.
Yeah, that's the mark of the industry.
Yeah.
So I mean, to throw some extra detail in there, the simulation that we ran there was run on a desktop from 2017. It was a nice desktop in 2017, but it's a desktop from 2017. Yep. It ran at 250 micron resolution, and it ran in 17 hours. The large part, we ran that one with a 800 micron resolution, and that ran the thermomechanical simulation in 6 hours on that same desktop.
Wow. So 6 hours, and then printing that is
a week. or more.
So, and I don't know, order of magnitude less.
I'll add that these performance statistics are highly dependent on the hardware, so the code is extremely parallelized. So if you have a better desktop than that, with a few times as many cores as Daniel ran, it'll utilize that, and you'll see performance gains. So we can on hardware here, we could run things much faster than on Daniel's old desktop. But
And Daniel, just a bit of context, like we kind of showed a small part, we showed a big part. In general, where are you applying this tool? What have you seen as the most effective use of a tool like this?
So the most effective use of this tool really is on our Sapphire XC, right? So for smaller parts, it's still valuable, right? And it can run quickly. The smaller the part, the faster you can run it. That's always the case with these things. But with the Sapphire, a lot of parts can get away with things like scaling. And that's sort of what that picture of the muzzle brake was showing, where scaling solves problems where you have a relatively uniform shrinkage, which happens on a lot of small parts that are relatively rigid. But when you go to these larger parts, you can't just scale it and get to the part that you want. And it's not just by some small amount either, right? Like we're talking, a quarter of an inch deflections on parts where, that's just not functional in a lot of cases. And so we need to be able to see where these deformations are, see where we need to add supports, and do it before running through this cycle of printing parts, right? Because again, with small parts, you can take a chunk of it, you can de-risk it, you can run it in a couple of hours and see whether or not you're going to fail or succeed. And that's, something that we've been doing. Trial and error is a reality of the additive industry for far too long. And the problem is that, as you get these bigger parts and bigger problems, the problems don't scale down into a test cell type setup. And they show themselves on these parts that cost, tens of thousands of dollars to print. And so no one wants to do that more than once. And so that's sort of what we're targeting here is, we need to be able to say, this is going to succeed and get you a part that you can use at the end of it, right? Because it's one thing to print it successfully, and it's another thing to have a part that you can use, right? And so the end goal is a part that you can use, and that's where.
I like to add, not only you can see how the part will deform, but I can also see hot stress spots. So if material, sometimes you can even have fracture during the build. So the software can highlight where they have high stress concentrations, where it's likely to have a fracture. And then you could run either design modifications or try to do different iterations in the process so that they can actually reduce the stresses. So have a successful print in terms of getting a part that didn't break during the build. So.
Yeah. And I know not a lot of printers these days see the same part day after day after day. It seems like a lot of these printers are getting different geometries thrown at them consistently. So something like this, you might have 15 different parts a year that you're running, and at the prices you're saying, that's like you could be exposed to $300,000 or something in revenue. That's a lot of value that could be on the table if you're able to kind of foolproof this process.
Yeah, I mean, it's even more than that. A lot of our customers have these machines, and they are, working on, in the machine shop environment, it's basically a different part every time you print. And so you might see a different part every week or multiple parts every week, right? And so the promise of AM has always been, you don't have a bunch of tooling, right? You have a part you want and you print it. But we need to be able to live up to that promise by knowing whether or not you're going to have a good part and being able to get to a good part without having, something like I've got years and years of experience and millions of dollars worth of printed parts sort of rattling around in my head. And that's not scalable, right? I still don't get it right all the time. That's, I get it wrong. And so that's where simulation really comes in and helps, is that, it gets us answers that are based in reality and not just experience.
Well, and you kind of mentioned your Sapphire XC. I mean, the Sapphire XC only came out a couple years ago, and now we've got alloys coming out every couple months. And like at some point in time, the pace of this innovation, you can only have so much experience. It's impossible to have 10 years of experience on a Sapphire XC printing copper.
Right.
Nobody has that. So it's nice to be able to have a tool like this to go in and sort of troubleshoot some of these issues even before you print anything.
Yeah, if I could add, user experience can be more of a qualitative fix into something. Many times you learn that if you build a flat surface, it creates a shrink line. But experience does not tell you how much it will shrink. So software can tell you, okay, it's going to shrink by so much, and then you can actually compensate for that. So it's beyond just experience alone cannot solve this. It can help you, but you anticipate the issue, but it's hard to solve it. So even with a lot of experience.
Yes, and then it just going off of the qualitative experience, you end up being very conservative, right? Because again,
Correct.
when you're printing a part that costs $100,000 to print and finish and all of that, you want to make sure that it succeeds. And so in the end, what you end up with is things that have more support than you really needed just because you needed to make sure that it worked. And then so now on down the line, it needs more machining, it needs more handwork, it needs more inspection. It's, you know, there's just all of these costs. So it's more expensive to build a good part without this, just because you have to be conservative, even if you are successful.
That's a good point. And we kind of talk about the value here. You mentioned something about the computer you're running on. Can you walk us through the workflow that you would follow to use the software? Like, where does this come in to your workflow?
Sure. So for me, I'm not working on the design side of things. So for the most part, I have a part that somebody wants to print, and I bring that into Flow. I set it up to the best of my knowledge, and then I will take that and slice it, and then I'll open that up in our software called Inspector, which is another part of Flow. So after we've sliced it and generated all the laser instructions, we know exactly what the printer is going to do with that part, and then we can basically hit File Export to PanX, and Flow will generate all of the inputs that PanOpt needs, and we just go run that simulation, and then you have the results in minutes to hours, depending on what you're trying to solve.
And we've mentioned this part, this micro turbine part. There's also a heat exchanger that you've had some real world experience on, and could you walk us through some of that, what you saw there?
Yeah, so this was actually one of our first forays into dealing with the guys over here at PanOpt. Is we had this heat exchanger that we were printing in-house, and they were looking for a really complex part, and so we threw this part at them that was basically a full volume of Sapphire. So we're talking, a 12-inch part or something like that is filled with 150 micron fins. So a few thousandths of an inch on the inside, and on the outside, we had relatively few supports because we wanted to be able to take this part and just clean it up very quickly. So one thing that we had was when we printed the part, we supported this flange that sort of started separately with supports that were parallel. And so you can see here, basically these supports, when we started building the flange, the whole support was able to flex and walk around and virtually would scrap most parts. Being that this was our in-house part, it was a test part, we were able to machine that back flat, but the back side of it is just as messed up as the front side. Fortunately, we only need it for clamping and not high pressure, so we were still able to use it. But the cool thing was when they came back to us with the simulation, their first question to us was like, hey, we saw this like sort of crazy thing going on here, and we're not sure if this is an artifact of the simulation or what's going on here. And I was like, hold on, let me grab a picture of the part, and I showed them that. And that's where we it's kind of where we started.
Yeah, we've been friends ever since.
So what's going on here? I mean, is there like a shift line in there? But the thing is, it looks like it's bent.
Yeah, so essentially the bottom of the part is separate from the rest of the part behind it, and so it started building, and the heat is actually just sort of moving the part around in the powder bed. And so that sharp line that you see is actually where it connects to the rest of the part. And then it gets rigid from there because it's solidly connected to the build plate. But the problem was that these thin, tall supports were able to just walk around as we were building it.
Wow, and that took everybody by surprise. It sounds like nobody anticipated that. But the software accurately predicts it, and you can, I mean, see exactly it's correct, or it's going back to the normal, even at the right spot.
Yeah, I do want to just reiterate that while we don't have permission to share the inside of that thing, it is all being meshed. So that's like, I think, I don't recall off the top of my head, somewhere around 80 to 100 million node FEA mesh. It runs in about 7 hours on my 48 core desktop in the next room. And for scale, I don't know, I can't remember if you said this already, Daniel. I think it's about 300 millimeters long, right? So it's quite, it's not small.
Mm-hmm.
Yeah, the Sapphire build plate is 315 diameter across, and if that thing's full size, I mean, it's it's roughly 12 inches, and for using inches. Now that's pretty impressive. And so with this, I know we're not going to give quotes or anything here, but Erik, can you give us like a relative investment that somebody would take for this to have this solution?
I mean, we tried to price it such that you get most of the investment or all of the investment back based on what you guys had estimated an XC failure might cost somebody. So I think that's a good high level descriptor of it.
Yeah, I would encourage. We offer free trials, month-long trials for people to try the software, and encourage people to send us an email, info@PanOptimization, and we'll set them up.
It's really and you can't really. I can try to articulate at a high level, how big 100 million nodes is, or how this multi-grid scales linearly. But you just can't. You have to, it's something you have to get your hands on and experience to really get. I think so. I would encourage anybody who's interested to take us up on that offer.
I think anyone who's had a large print get halfway through and not be able to complete it, I mean, the pain is there. And if this is a way to sort of mitigate that risk and get success quicker, and to iterate on the software side rather than having to take a multi-million-dollar piece of manufacturing equipment, and now you can use it for something else. You can use it for something that's a known good part. Get your revenue built on that. There are a lot of value streams that this creates. I'm pretty excited about it. And Daniel, you've used this a couple times with a copper as well.
Mm-hmm.
What do you say? Is there anything different when you use this for different materials, or is it pretty much operating about the same?
Yeah, so I mean, it under the hood, it all works the same. Right? We have calibration files where we input basically the physical parameters of the material, and for most of it, we just start with the actual measured physical parameters of material, and that's that, right? And then we just sort of measure heat losses in various places, and we measure what some sort of reference parts look like, and that generates the sort of baseline material parameter, and so that is just a handful of numbers that you change between each material. So it works essentially the same. Now, that said, with copper, we sort of have a separate issue where our throughput is high enough on copper, and it has some interesting properties that at not even a terribly high temperature, copper starts sticking to itself. It's not quite sintering, but it's enough that it starts changing the printing process. And so what we have to do is we have to reduce the amount of power that we're putting into the part so that the machine could go faster and it could go hotter and all of these things, but copper doesn't like that. And so we're able to use PanOpt to say, here's where we need to put less heat into the part. We slow down a little bit, and we let it keep running, and we get much more consistent parts out of it without any of the issues of copper sort of sticking to itself.
No, it's good to hear the real world examples on this. And Pan and Erik, congratulations. It sounds like you developed an amazing tool. We are at the 30-minute mark, and I would love to get some closing thoughts from you, and maybe we'll just go around the horn. But Pan, if you want to kick us off. Yeah,
I'd like to say thank you, Bella. We've been working almost 1.5 years, and it's been a great team to work with. So thank you.
Yeah, thank you as well. Erik?
Yeah, I'll offer similar sentiments. So thanks so much for Velo for all of the support. I mean, lot of engineering resources to harden the tool. Quality of the application engineers we've worked with has just been excellent, and it's been a really fun engagement. And now you're doing some marketing for us, which we also appreciate. So it's been great.
Well, I mean, the synergy of these two products is fantastic. Just having the ability to go in, test the part without having to print metal. I mean, that's ideal, I think. But Daniel, any closing thoughts from you?
I mean, it's been great to work with, and this is sort of solving, I think, one of the big open problems with with what we've been working on here at Velo is, we can print all of these geometries, but we can't print every geometry ever, right? And so that's where we need to figure out where are the bounds, and how can we make it better, and how can we put this in the hands of people who don't necessarily have as much experience, right? Because that's what everyone wants to get to, is we need to print more parts and print more good parts, and this is the road to get there.
Awesome. Well said. All right. Well, thank you all for joining us today, and thank you, audience, for joining us as well. We're going to have this show be available on our YouTube channel, so you can watch recording anytime you want. We do have a library of these shows. This will be our 37th, so you've got 36 shows to catch up on if this is your first one. But always looking forward to hearing from our audience. And again, thank you all for joining us. And with that, we'll let you get back to your day.
Thanks.